Hello everyone, welcome to part 2 of this video series looking at exam questions from the standard level IB Maths AA course. My aim here is to give you some tips and tricks, exam technique that helps you answer questions in the exam. I'll hopefully be following up with some more deep dive videos looking at particular skills used to answer these questions in the future. If you're interested in some tutoring, I also offer that through my website. You can find the links to all these things below. Hope you enjoy the video.
So today's question is looking at a couple of different functions. We can see here we have a reciprocal function in part 1 and an exponential function here in part 2. A little bit of transformation, a little bit of calculus using the chain rule. So let's get stuck in. First off, we have the reciprocal function here, f 1 over x minus 1 plus 2. Note that we're given a specific domain for this function between 1 and 4. Now it says write down the equation of the horizontal asymptote in the graph of f. First of all, it's a write down question. This should be fairly straightforward, but we do notice that it's actually a 2-mark question, so perhaps there's a little bit more going on. Firstly, a couple of ways we can do it. One is we can sketch the graph thinking in terms of transformations. We know generally what the shape of a reciprocal graph looks like. It's a pretty poor sketch, but you get the idea. In this case, of course, we have a transformation applied, or 2 transformations applied. We can see that a -1 in this position is going to shift the whole graph 1 unit to the right, and a +2 here is going to shift the whole graph up 2. So with that in mind, we can see that instead of having the usual reciprocal graph which has a asymptote at y equals 0, this is going to be shifted up 2 units for an asymptote here at y equals 2, and it's going to be shifted 1 unit to the right, so our vertical asymptote is actually going to be through here at x equals 1. So the graph will look something like this. Once again, this is just a sketch to give us a general idea. So the horizontal asymptote is going to be through the y-axis here at 2, giving us the equation y equals 2. Now this might give us a hint as to what our 2 marks are for, not just writing 2 but expressing the answer as an equation. Another way of thinking about this, of course, is the idea of limits. We can imagine what is the limit of this as x tends to infinity. Well, when we have 1 over infinity minus 1, essentially, of course, this part becomes 0, so we can ignore it, and we're left with our 2. So a little bit of thinking either about limits or about transforming of the graph. Next, we're asked to find the derivative f prime of x. Well, here we've got a slightly tricky part, but if we rewrite the first term as the bracket raised to the power of -1, things become a little bit easier. It's always a good idea here to be really clear about when you're dealing with your function and when you're dealing with the derivative function. So changing from f of x to f prime of x, or f dash of x. Well, we simply use the chain rule, so we multiply the bracket by the power and then reduce the power of the bracket by 1, remembering that after we've done this we need to multiply by the derivative of whatever is inside this bracket. Again, you can be more formal about how you use the chain rule here, but I think in this case it's fairly straightforward. We're going to multiply by 1, but of course we normally wouldn't bother writing this term, just here for clarity of multiplying by the derivative. The 2 drops out, and we're left with minus 1 over x minus 1 squared. You can leave that in the index form as it is here with the -2, or you can write it as I have 1 over. Not too much difference here. Okay, so that is our derivative. Now, moving on to the second section, dealing with the exponential function. Get a bit more space for this. We have a function g, again transformed to exponential, and the graphs of f and g have the same horizontal asymptote, remembering from the first section that the horizontal asymptote of f was y equals 2. Now, again, we've got a write down question, writes down the value of b. It should be fairly straightforward as to finding what b is. Knowing what we know, again, just a quick sketch. So we've got the picture in our head, a general exponential function does this, crossing through the y-axis at 1, having a horizontal asymptote at y equals 0. Now, our a value in this function is going to be a vertical stretch, either stretching or compressing the graph, depending on whether a is greater or less than 1, and b is going to simply move the whole graph up. So if I want my horizontal asymptote to, instead of being here at 0, in fact be here at 2, then I'm going to have to shift the whole graph up by 2. So writing down the value of b should be 2. Then we are told that the derivative at 1 is negative e, and we're finding the value of a. So you can see here these two questions are leading you through finding a and b based on some properties of the graph. Now, if the derivative at 1 is negative e, then we need to find an expression for the general derivative function g prime of x. We're going to do this by differentiating, recalling that the exponential function differentiates to itself, and so we merely need to apply the chain rule here to multiply by the derivative of the power. So we take a times e to the negative x, which of course differentiates to itself, and we simply need to multiply by the derivative of negative x, which is minus 1. b again differentiates out. So if the general function, the general gradient function g prime of x is negative a e to the negative x, I can now substitute in 1 to get negative a times e to the negative 1, and all I need to do here is equate that to the given value, which was negative a e to the negative 1. So it looks a little bit tricky, but I think if we just start applying the usual techniques for solving equations, we should be okay. Multiplying through both sides by, I think that probably the easiest thing to multiply through here is negative e. That's going to do two steps in one. One is get rid of the negatives on both sides, and also multiplying through by e is going to turn my e to the negative 1 here into 1. So that's going to be quite nice to do. On the left hand side, I now have e squared, and on the right hand side, e to the negative 1 and negative e. With this negative out front, just cancel through to a. So actually, despite looking tricky, not too bad, we end up with a is e squared. This will allow us to now go back and rewrite either the original function, g of x being now e squared times e to the negative x plus b, which was 2. Now that first term needs tidying up, so we can just use our index laws here and add the powers, so we get e to the 2 minus x plus 2. We can also rewrite the general form of the gradient function g prime, which now becomes negative e to the 2 minus x. Okay, so using those, we should be able to answer the final part of our question, which tells us that there is a value of x for which the graphs of f and g have the same gradient. Find this gradient. Now, worth noting, we're finding the gradient, not the value of x at which this occurs, but finding the gradient at that point. So let's try and think about what's going on. We've got a graph that looks like this here for f, and at some point along this graph, the gradient gives us exactly the same value as it does on the graph of g. Now, it might not be immediately obvious where this is, but the algebra can tell us. All we're going to need to do is equate our equation for g prime and our equation for f prime here. So we have negative 1 over x minus 1 squared, negative 1 over x minus 1 squared, and we're going to equate that to g prime, which was negative e to the 2 minus x. Right. Now, looking at this equation, it should become apparent that this is not something we're really going to want to solve by hand. As this is from a calculator paper, we're going to take our GDC, we're going to use it to graph this side of the equation as one of our functions and graph the other side of the equation as the other function. This is, of course, a really powerful technique. It allows you to solve any equation using your GDC. So I'm going to go ahead and throw those two into an online graphing package, and we can see where these two graphs cross is going to be the solution to that equation, or in this case I should say solutions, because I can see that there's a region here where the graphs are crossing and one here. Now that gives me pause for thought, because if we return to the original question, it does say clearly there is a value of x, but my graph seems to suggest 2. Now the reason for this is of course this original point here that we made at the beginning, that x is restricted, the domain of the original function f is restricted to between 1 and 4. Remember, when they give you information in a question, it's always going to be relevant somewhere. Now this piece of information didn't come in into the last section, but there we go. So returning to our two graphs, we can get rid of this solution down here because this is in the region below 1 on my x-axis, of course, here. Oh dear. This is the solution that we're interested in, and by tracing along or using the intersect function on your GDC, you can see that our solution here is at 2, -1. Now let's just think about what that means. 2, the x value, is the value of x, which is making these two gradients equal, and -1 is the value of the gradient. So returning to our question, it said find this gradient. That is going to tell us that the solution we want is -1.